Class example 3.62. Use an algebraic process to solve each of the following equations. Verify both numerically and graphically. Okay, so in these equations, we see that we have logarithms on both sides of the equation. So this is going to be one of those drop the logs type of logarithmic equations. So let's use any log laws that we can to combine multiple logarithms. So on the left side, we can use our second log law to write it as a single logarithm where we're dividing. So we went 9 minus 2x divided by x minus 2. And we were able to do that because we were subtracting. Now at this point, if we think about it, if log of this is equal to log of x, if they're actually equal and the log is the same for both of them, the same base, then the insides must be equal to each other as well. Or you can also just think about this as dropping the logs at this point. So now we can just set 9 minus 2x over x minus 2 equal to x. If we multiply both sides by x minus 2, then we'll end up with this equation. Now distribute the x into the brackets. Get everything over to one side and then set it equal to 0. And now we can see that this is a difference of squares. So perfect square, and we're subtracting, so difference of squares. So we can factor that as x plus 3 times x minus 3. So our solutions here, potentially, would be x is equal to negative 3 and x is equal to 3. But now we need to check for any extraneous roots. So let's try throwing in negative 3 into the original. So negative 3 into the original. So this would simplify to the following, where these two logarithms end up taking the log of a negative number. So x is equal to negative 3 has us logging negatives, which is not allowed. So x is equal to negative 3 is extraneous. So let's try x is equal to 3. So if we try this one, we're not taking the logarithm of any negative numbers, and we can actually check to see if this works, and we do end up getting the left side of the equation equal to the right side of the equation. Now let's verify graphically. So in this case, we brought the log x over to the left side of the equation and set our y2 equal to 0. Now in this case, it might act a little different than what you're used to. Most of the time it would already be on the first curve. This would be what shows up, but then that might not be. So you might need to use the left and right arrows to scroll over until you're actually tracing on the blue curve. So now when it says first curve, now we can push enter. And then we'll find that our intersection is at 3. All right, let's look at the second one. Now we could, at this point, combine these under a single logarithm, but what I would recommend is getting any terms with a variable in it, so x, get those to the same side first, and then combine them. So let's bring this logarithm over to the left side of the equation. And now at this point, we can combine these logs. So this time we're adding. So we're going to combine these by multiplying. And now at this point, we could expand the inside of the logarithm first, Or you can do it after we drop the logs, either way. So this time we're going to drop the logs first. And then we'll expand. And simplify. So getting everything equal to 0 on the right side and then bringing everything else to the left side. And then we'll factor. So we have one solution of x is equal to -1. And another solution of x is equal to 4. Potentially. Because you probably saw this coming, now we need to check. So if we throw in -1 into the original equation, so in place of all the x's, then we find that we're actually not taking any, the log of any negative numbers. So far so good. And if we check, the left side of the equation is equal to the right side of the equation. So x is equal to -1 is a solution. So now let's check the other logarithm. Or the other solution, x is equal to 4. So this time, when we substitute 4 into the equation, we'll see that we again end up taking the log of a negative number. So x is equal to 4 is extraneous. If we graph this, we'll see that we end up with one solution of x is equal to -1. An alternate graphing method would be to set the equation equal to 0. So in this case, we could bring both of these terms over to the left side of the equation. And then setting the other side equal to 0. But then we would just need to just put into y1. And then we'd find these zeros. So really you're finding the x-intercepts on your graph at that point, because you can also think about that as the line y is equal to 0. It'd be the same thing, right? Now, this might look really confusing, but what we've done here is just shown this with a change of base method. So let's just look at this first part here. Log of 2 minus x over log 2. Well, that's just this part, right? Log of 2 minus x over log 2. Okay, so this would be if you had like an older calculator, you might use that method. And then the next part, log of 6 over log of 2, and so on. Now in this case, if we're just finding the x-intercepts, then we're going to find the 0 on your calculator. And again, we'll find that we have one solution at x is equal to -1.